Okay, so today we will be continuing our discussion on the electric potential. Do you have any questions before we start? Any questions about the things we had discussed or the definition of the electric potential?
Can we just say that the electric potential is just amount of potential energy on the charge?
Well, the electric potential is not the, in a sense, yes, in the sense that suppose you have a given charge distribution. It will create a potential at every point. And if you put some unit charge in that point, if you take it from a point that has zero potential at infinity, let's say, and bring it to that point, then the potential energy of the system as a whole will change by the potential at that point times the electric charge. In that sense, the potential of a point is the amount of potential energy per unit charge of the system if you put that charge over there. Other questions? And also this was the definition, if you remember the definition of the electric potential. The electric potential at a given point P, let's say, this is equal to minus the integral of the electric field from a reference point P0 up to our point P. This is the change in the potential between P0 and P, the difference of the potential between the point P0 and the point P, plus we add the potential of the point P, P0. This is the definition of the potential at a given point. Now let's look at how the potential changes from a point to another point. So for example, we can say that we can take this point P0 and let's imagine this other point P, which is very nearby. Let's denote this vector by dl. Or you can just imagine this one, this way. So you are in a region where there are some electric charges somewhere and you are measuring the electric potential at different points. You take one of your points at the tip of one of your foot and you just step up a given length or to some other direction, and at every point you measure the difference in the potential. Let's say your length, the length of your step is fixed. You change your direction and see how the potential changes from point to point. Now this expression already tells me what is the change in the electric potential, so we can just say that the change in the potential is equal to minus E dot dl, which is minus the magnitude of the electric field times dl times cosine of theta. I will use dl and delta L interchangeably. I mean, they basically mean the same thing. So let's see. Let us suppose that we keep delta L fixed. Okay, delta L is fixed. So we just step in different directions. So basically theta will be changing, and hence the measured value of the change in the potential will also be different. Now what is the maximum value of delta V? So we are just measuring the potential differences between these 2 points. You can just imagine you are taking steps in various directions and measuring the potential difference between your original point and your next point. What is the maximum value of this quantity? When cosine is minus 1, that is the maximum value of the change. When cosine is minus 1, so the maximum value of delta V is E dot dl. So assuming you know the potential at every point, so you choose some point and then consider the potential at nearby points. So the potential between these 2 points, in general, it will be different. Delta V will be different. So you find a point at which this change in the potential is maximum. Well, that direction, well, you are determining the direction of delta L basically. That direction is in the opposite direction of the electric field. Do you agree? Because the maximum value of delta V is when cosine theta is -1 for fixed delta L. There are some charges, electric fields are fixed, so I'm just measuring the potential difference between different points. For fixed delta L, delta V is maximum if cosine theta is equal to -1 or theta is equal to pi. But remember what theta is in this definition over here. Theta is the angle between E and dl. So you just measure, you take one point, consider the other points, measure the potential difference between these 2 points. The potential difference there will be a point at which the potential difference is a maximum. This is the other point. So this is the direction of dl. And for this point, for which delta V is a maximum, the angle that this direction makes with the electric field is pi radians or 180 degrees. So this direction makes 180 degrees with the electric field. Do you agree? Do you agree, the ones on the back? Or some reaction? Okay, that is one reaction, but kind of indeterminate reaction. Do you agree or not? Just imagine this way. You are on a region where there are many hills. So you are taking one step in various directions, and you are trying to determine how much your height changes. That is exactly what we are doing. Instead of measuring the height, we are measuring the potential difference. And in each, we just consider all the points around us, which are close by, and we find a point for which, if we step in that direction, our height changes maximum. So let's say we are on a hillside, let's say. If you step this way, your height doesn't change. If you step this way, this is the hill. Your height goes down. The change in your height is negative. If you step this way, that is the maximum change in your height in the positive direction. We do the same thing. Instead of the height, we have this potential. So we just take one point and consider all possible dl vectors. So that it can be pointing in this direction, in any direction that you can imagine. And for all those dl, we measure the potential difference between P0 and P. Well, this expression already tells me that this one over here is our potential difference. But if dl is short enough, small enough, the electric field doesn't change between the point P0 and P. It's the same electric field. Eventually we will assume that this delta L will be almost infinitesimal. So we can just remove this integral, or we can just take the electric field out. Since electric field within this path is constant, I can just take it out. What is left is just delta L, the change in the position between those 2 points. And I have the scalar product of 2 vectors, and the scalar product of 2 vectors is defined as the product of their magnitudes times cosine of the angle between the 2. And this tells me that the change in the potential is maximum if we are moving away in the opposite direction to the electric field. Okay, some reaction. Okay, just nod your head. But you see, if we want to define the electric field, we have to define 2 things. One, we have to define the magnitude, and then we have to define the direction. But we had already found the direction of the electric field by just looking at the potential. We just found the direction in which the potential change is fastest. The electric field is in the opposite direction. So potential itself carries the information about the direction of the electric field. So we know the the potential does have this information about the direction. Now, the next thing we have to identify the magnitude of the electric field. But if we know that if we determine the direction, so we just choose our dl vector in that direction, in the opposite direction, let's say. So cosine theta is -1, and delta V max is equal to minus E times delta L, but then we also know E. So although we define the potential in terms of the electric field up to this point, so if we know the electric field, we said that by just evaluating this integral over here, we can calculate the potential at every point up to one unphysical unknown. But we can also go the other way around. If we know the electric potential every point, then we can determine, for a given point, we can determine the direction in which it changes the fastest. The change in the potential would be the fastest. The electric field is in the opposite direction, and this is nothing but we have a minus sign over here. And this is nothing but the derivative of the potential in that direction. So we know, given the potential, we can determine the electric field, both its magnitude and direction, in terms of the potential. So in a sense, potential and electric field, they contain the same information. Given one, we can evaluate the other one. The two descriptions are equal to each other. We will not be losing anything if we concentrate on the potential. We will not be gaining anything if we concentrate on the electric field. They are equivalent mathematical objects. They carry the same information. We can go from one to the other one. Now, the nice thing about this thing is that most of the time it's easier to determine the potential than it is to determine the electric field directly. For example, we have been discussing these simple systems where we have, let's say, one charge and 2 or 3 isolated charges, or we have one charge inside a conductor, or we have these cylindrical objects that are easy to study. But for the other problems, we will not be discussing them. Like, for example, what about the charge, I don't know, a cube? If you have a charged cube, what is the potential everywhere? Well, calculating the charge conducting cube, let's say. Where will the charge be? The charge distribution will not be uniform, etc. So that will be a tough problem to determine the electric field directly. But determining the potential energy would be much easier. And once we determine the potential, not the potential energy, potential, once we determine the electrostatic potential, we can determine the electric field. There won't be any problem. Now, of course, this procedure that yes?
Why do we have still minus sign potential at
Oh, true. This is the magnitude. Now, this procedure over here to determine the direction of the electric field, okay, it will work, but it's kind of tedious. I mean, you have to just look all around a given point and to determine the direction. We usually don't do it this way to obtain the electric field. Let's look at this one. Delta V is always equal to minus E dot dl. If you consider 2 very small points, very nearby points, this will be always true, whether dl is in the direction of the maximal change or not. And this will be valid for every dl. And this delta V is, let's say, it's the V at the point x, y, z, and x0, y0, and z0, and x, y, z is equal to x0, y0, z0 plus dl. So is this notation clear? So this just tells me that x should be x0
plus the x component of dl, y is equal to y0 plus the y component of dl, and z is equal to z0 plus the y component of z component of dl.
Whatever dl vector you consider, this equality has to be true. Now let's take some special dl vectors.
Like dl vector, let's just assume it is this one.
I just take one particular dl vector. Now this relation should still be true for this vector. This relation is true for every small enough dl. Well, if this is my vector, so I have the x is equal to x0 plus dl, y is equal to y0, z is equal to z0. So v of x0 plus dl, y0, z0, minus v of x0, y0, z0. This is equal to minus, well now E dot dl is just the x component of the electric field times dl, the x component of dl. So this difference, the potential difference, is equal to minus Ex times dl. So what I did, this relation I said that it is true for every dl. I chose one particular one. And since this is true for every dl, it has to be true for this one also. But if it is true for this one, I just rewrote this expression. Now for this dl, y and z doesn't change, y0, z0. X is x0 plus dl here and x0 over here. So I'm just looking at the 2 points along the x-axis. Now 2 points that differ only by their x-coordinate. And I'm just looking at the potential difference. Well, I can just divide everywhere by dl.
So what I obtained that Ex is equal to v of x0 plus dl, y0, z0, minus v of x0, y0, z0 divided by dl.
This would be true for any small enough dl.
Let us just take the limit as dl goes to 0.
Now what is this? This should be familiar to you, this limit. I have a minus sign over there. It's just a partial derivative with respect to x0 or x. So the electric field at the point x0, y0, z0, this is equal to minus the derivative of the potential with respect to x0, evaluate that x0, y0, z0. Let me just drop this zeros.
So the electric field at the point x, y, z is equal to minus the derivative of v with respect to x.
So again, given the potential, you can obtain the electric field by just taking its derivative. Well, I can do the same thing for taking dl in the y direction or in the z direction. The derivation will be just identical.
So Ey is just minus dv by dy, and Ez is minus dv by dz.
So given the potential, we can calculate the electric field. All of its components or its magnitude and direction, whatever you want. This notation. Well, this is the electric field at the point R, whatever that point is the derivative of the potential with respect, the x component of the electric field at the point R is the derivative with respect to the x of the potential. And you have to evaluate this derivative at this point and multiply it with -1.
These equations, they don't tell us the direction, right?
They do. You determine all the components. Once you know the components, you know the direction.
The potential is a scalar quantity.
The potential is a scalar quantity, but nevertheless, it is changed with respect to which point you are considering. It tells you the direction. You see, the electric field is always in the opposite direction to the direction that the potential increases.
The change is what tells us, so the change is what tells us the direction.
Yes. So if you are moving in the opposite direction to the electric field, then potential increases a maximum for a given distance. Or put it the other way around, if you calculate in which direction the potential changes the fastest, the electric field is in the opposite direction. Let's do an example. Electric field of a point charge. So we have calculated the potential of a point charge using the electric field. Now let's just do the other way around. We know, let's assume we know the potential of a point charge, which is, what is the potential energy of a point charge Q located at the origin? Oh, this is one of the expressions that you have memorized all your high school years. Now remember it. Now we know the charge. There's a charge Q at the origin, and I want the expression for the potential over here. What is U, if you say U over R? Q over D. Well, the distances are 1 over 4 pi epsilon 0. There is no trick in the questions. Now, we were discussing with a friend that one of your problems seems to be you are always looking for a trick in the question. Nature doesn't play tricks. It might be tough or easy, but it doesn't do tricks. So, no trick. The potential energy, potential created by a point charge at the position R. This one. Now, let's try to calculate Ex. And remember, R is equal to square root of x squared plus y squared plus z squared. Now, Ex will be minus the derivative of this potential with respect to x, which is equal to minus 1 over 4 pi epsilon 0 times q, the derivative of 1 over r with respect to x. Now let's use the chain rule. Minus q over 4 pi epsilon 0, derivative with respect to r of 1 over r, times the derivative of r with respect to x. Minus q over 4 pi epsilon 0. What is the derivative of 1 over r with respect to r? Minus 1 over r squared. Now we have to take the derivative of this expression with respect to x. Again, we can just use the chain rule. The derivative of this thing with respect to its argument would be just with respect to this x squared plus y squared plus z squared, it just gives me 1 over 2 square root of x squared plus y squared plus z squared times the derivative of x squared plus y squared plus z squared with respect to x, it gives me 2x. Now the 2's I can just cancel, this minus will cancel this one. This is q over 4 pi epsilon 0. This square root is nothing but r. I already have two factors of r, there is another one, so r cubed, x over r cubed. This is ex. This one. Well, this is just a chain rule of derivatives. My function is a function of r, which is a function of x, y, and z. So I'm first taking the derivative with respect to r, then taking the derivative of r with respect to x. Now we have to repeat this for y and z. But you see, if you want to take the derivative with respect to y, the only thing that will change is that here I should take the derivative with respect to y. And the only thing that will change is instead of 2x over here, if I take the derivative of this quantity with respect to y, I get 2y. So Ey is equal to q over 4 pi epsilon 0, y over r cubed. And Ez will be q over 4 pi epsilon 0, z over r cubed. Now let's write the electric field. This is Ex in the x direction, Ey in the y direction, plus Ez in the z direction. This is equal to q over 4 pi epsilon 0, 1 over r cubed. This is common in all of them. I have x in the x direction, y in the y direction, plus z in the z direction. Well, what is this vector? It is nothing but the position vector of the point that I'm studying. So this is nothing but the r vector. So the electric field is q over 4 pi epsilon 0, r over r cubed, or q over 4 pi epsilon 0, 1 over r squared in the r hat. Because r hat is just r vector divided by its magnitude. So once we know the potential, we know the electric field. And now I lost 2 points in the exam. So that is my electric field. So given the potential, I can determine the electric field. Now, one nice thing about the potential is that it's a scalar, as your friend pointed out. It's just a number. It's not a vector. So when we are adding the electric field vectors, we have to add them vectorially. But when we are adding these numbers, they're just numbers. You don't have to pay attention to the direction information. But somehow, the direction information of the electric field is still contained in that sum. Now, any questions on this example? Let's do one more. I will do one more example. Now, if you remember when we were discussing the dipoles, we had, let's say, a plus q charge over there, a minus q charge over there, and we had studied only the electric field at 2 points. Along this line that goes through the center or along this axis. Those were the only 2 points that we had studied the electric field of. Because those 2 points are easy to evaluate because we know the direction, we can visualize the direction of the electric fields created by each one of them, so it's kind of easy to add their components. But if you want to find the electric field here, well, let's see, this one will create an electric field in this direction, and this one will create an electric field in this direction. So what will be the direction of the net electric field? How do we add the components? Of course we can do it, but it will be hard. But for the potential, we don't have to worry about these 2 things, about the direction, so we can just add the directions. So let's try to calculate the potential at the point P. Because if we can determine the potential at the point P, by just taking the derivatives, we can calculate the electric field everywhere. Now let's say this is our R1, this is our R2 distances. So in terms of this R1 and R2, we can write the potential. V is equal to 1 over 4 pi epsilon 0 Q over R1 plus 1 over 4 pi epsilon 0 minus Q over R2. So we can just combine them. This will give me 1 over 4 pi epsilon 0 Q times 1 over R1 minus 1 over R2, or this will be equal to 1 over 4 pi epsilon 0 Q times R2 minus R1 divided by R1 times R2. This is the potential. And, well, in general, in the places where we use this dipole, we usually have these charges over here, and we look at the potential somewhere over here, in the sense that this distance is much larger than this distance over there. So let's just assume that this is our D. The distance between these two are D. Let's say this is the midpoint. This is R. And D over R is much, much less than 1. Now, if you just imagine that 2 of your friends sitting next to each other just on the last seat over there, they are holding the 2 ends of a string, and I am here holding some point in the middle. So there's one string going to your friend over on the left, on my left, and another string going to your friend on the right. And there's these 2 strings. The angle here would be very small, almost 0. And so this is this angle is almost 0 if I'm very far away. If that angle is very small, I can just draw this line, this segment, such that this is R2 minus R1. Here I have an equilateral triangle. No, isosceles triangle. There's a triangle of side R1. This up to here is again R1. What is left is just R2 minus R1. But remember, these angles over here, they are just 90 minus half of this angle. But this angle is almost 0. So these angles are almost 90 degrees. Almost 90 degrees. Not exactly, but almost. If that angle is almost 90 degrees, well, let's also define another angle. This angle is theta. So if that angle is theta, the angle over here will also be theta. Do you agree? Well, let's see. This angle is also 90 degrees. Well, let me draw it a bit larger.
So here is my Q, here is the middle point, this is D over 2, so let me exaggerate it a bit. So from here, I draw this line, there is also this line, these two are 90 degrees, and then there is this horizontal path, this angle over here is theta. This is pi over 2 minus theta,
because this horizontal line is perpendicular to this one. This angle is 90 degrees. If this is pi over 2 minus theta, again this is 90 degrees. If this is pi over 2 minus theta, this over here is also theta. Almost. So if this is theta, then this equation, here I have a right triangle, R2 minus R1 is d times sine theta. Do you agree? From this right triangle over here, R2 minus R1 is nothing but the length of the side opposite to theta. So that is the sine function. Now R1 itself is almost R2, which is almost R. Well, why? Basically R1 will be something like R plus d over 2, no, minus d over 2 sine theta. But d is very small compared to R. This is R. So that tells me that the potential is 1 over 4 pi epsilon 0 qd times sine theta over R squared. There's questions in this derivation.
What's theta in line? I mean, you go an extra line.
True.
Theta.
Well, you see, now when we talk about the dipoles, we will be mainly dealing with, let's say, atoms. Small atoms or small molecules. One molecule over here, there will be some other molecule at somewhere else, the distance will be large. So we will be talking about what is the potential felt by this molecule over here due to this other molecule here. Let's just imagine, for example, the hydrogen molecule. The hydrogen molecule has a dipole, electric dipole. So it will have such a potential. So the dipole, we said that it has a direction. Here we have some electric dipole which points in this direction. And the magnitude of P is equal to Q times D. This one over here. And then we have this vector over here. And we want to look at the potential created by this dipole at this point. At this R. Now this is theta. And this angle over here is pi over 2 minus theta. The angle between these two vectors, there is a dipole over here. Its dipole vector is pointing in one direction. And I want to find its effect on this point R. And the angle between this point R and the dipole vector is pi over 2 minus theta. Now the reason why I wrote the pi over 2 minus theta is that V is equal to 1 over 4 pi epsilon 0 qd times R times cosine pi over 2 minus theta divided by R squared, R cubed. Now it looks like a funny way of writing the same thing, but you see I have the magnitude of one vector, QD, then I have the magnitude of this other vector, then I have the cosine of the angle between these two vectors. That is the scalar product. So the potential created by a dipole, I can write it as, well, this constant 1 over 4 pi epsilon 0 p dot r divided by r cubed. Well, here I have r squared. I just multiply the numerator and denominator by r. There is no r over here. There is one here. So I just think there is another one over there.
How can we know if the angle is 0 or 180?
Which angle? I don't know. I mean, this is quite general. I can just take any point r, and this will be the potential.
In any example we have, how can we know if it is 0 or 180?
Which one?
Between the field and the potential, the angle between field and the potential.
The field. Well, I mean, here yet I'm not using that. I know the potential. That is one. So this is the potential. If you want to find the field, let's say the x component of the field, this is, I know this one, I have to take the derivative with respect to x. I don't need any direction here or any other information. This will tell me, once I calculate the components of the field, it will tell me the direction of the electric field. I don't know yet. Or you can say that, what is the direction in which V increases the fastest? That will tell you the direction. But up to this point, I didn't make any assumptions. I just know what the potential of a point charge is. Here I have 2 point charges. I have 2 point charges, so to calculate the potential created by these point charges at a faraway point, I just sum the potentials created by each one of them. Here up to this point, everything is exact. Now from this point on, I assume that I am looking at it at the potential at a very far away point, so that I can write the potential in this form. Now, if I calculate the next term in this expansion, it will be, well, this is one. This is the expansion that I obtained. The next term, if I just consider this parenthesis, it will contain some factor times d over r. So let's say if the size of my dipole is, let's say, the size of the molecule, and I'm observing it at a distance that is 10 times the size of the molecule, so this will be just 0.1. And it will be just a 10% correction to this expression. In general, we will be observing at distances 200 times the size of the dipole. Well, it's 100 times the size of the dipole. That is just a 1% correction.
What is this thing?
This one.
1 plus?
Well, you see, here we make some approximations. We said that, okay, R2 minus R1 is approximately d times sine theta. This is not exact. There, I should add some correction terms over there. And similarly, I said that R1 is equal to R2, which is almost equal to R. This is also an approximation. And in fact, if you just take this approximation, put it in this expression, it's not true, because this expression has corrections. And those additional terms that I ignored would just bring such a term. I don't know what this coefficient is, but I know that it will be proportional to d over r. And as long as d over r is, let's say, 1%, the correction will be of the order of 1%. So if my experimental measurement is not, the precision of my measurement is, let's say, 10%, I don't need to bother about calculating that one. I don't need it because I cannot compare it with experiment. What I will see is this one. If the precision is 0.1%, the precision of my measurement, then of course I need to calculate this one so that my expression will agree with the experiment.
For the area between dipole between charges, if you want to calculate the potential between charges in dipole,
What do you mean between charges?
I mean, E.
Okay.
We don't have R, just between C. We have charges
Okay.
between the potential between them.
I mean, you see, if you want to calculate the potential or the potential difference between 2 points, the potential will be the energy change in your system per unit charge if you bring an additional charge to the system, an extra charge to the system. So given this charge distribution, if you ask me what is the potential difference between this point and this point, that's infinite. Because R is 0, so these R's are 0. So the potential difference between those 2 points will be infinite. Because if I put an additional charge, a third charge at this point, well, I need to do an infinite amount of work to put it over there. Or if I put it right exactly at this point, again, I need to do an infinite amount of work to do that. Well, the between infinite minus infinite, infinite. But it doesn't make sense. So because you will not be able to bring a positive charge close to this one. And if you want to bring a positive charge close to this one, you don't need to do anything. But, I mean, at this point, classical electrostatics breaks down anyway. It doesn't make sense.
Even if one of them is double or triple the magnitude.
It doesn't make any sense. As long as you have this 1 over R, you should be away from R equal to 0.
How do you know that the correction is above expression? How do you know that the correction is below R?
A nice homework question. What is this coefficient? Now you have been doing these homework assignments about the Taylor expansion. The same thing. Just do the Taylor expansion and you will see that it's D over R. At least one of the terms I have ignored over here is, you see over here, R1 and R2 is not equal to R, but plus minus D over 2 times sine theta. This is R1 plus minus sine theta over 2 times D over R. Plus for R1 minus for R2 or the other way around. So you see, the correction is D over R. And I'm just throwing them away, saying that they are small. If there is another contributing term, this one is small. I can just throw it away. I cannot throw it away in this difference because that is the first contributing term, first non-zero term. That is why I cannot throw it away over here. So now we have the potential. We have to take the derivatives to calculate the electric field created by a dipole everywhere. Now you see, to take the derivative with respect to x and y and z, you can either write the dipole in terms of the x, y, and z components, or you can say that, let's see, if you consider this triangle, this is the z coordinate. This is x squared plus y squared square root. And this is x squared plus y squared plus z squared. So sine of theta is equal to z over, no, this is square root. Square root of x squared plus y squared plus z squared. So this is our v. V is equal to 1 over 4 pi epsilon 0 p over r cubed times z. Take the derivative with respect to x, y, and z, and you know the electric field at every point. Now before we had chosen some special points either along the axis of the dipole or perpendicular to the middle of it, but now from this potential you can calculate the electric field everywhere, not just on those special points. And this will be one other homework. Now, any questions? No, R is this one over here, square root of x squared plus y squared plus z squared. That is R. True, true. Exactly the same, just take the derivative. To take the derivative with respect to x and y, this is the only thing that depends on x and y. Well, to take the derivative with respect to z will be a bit more complicated because this depends on z and this also depends on z, but it's just the product, the derivative of product of functions. Questions? Just z is the coordinate z. There's no, the potential is not a vector. It's just a number. So if you want to calculate the potential at a given point, then you have to calculate, you have to know the distance from the origin, which is where your dipole is, and the z component of its position vector. Okay, see you after 10 minutes.